Good morning, my dear students. Today I'll discuss some practical that is incorporated in your syllabus of engineering chemistry. Today my topic of discussion is determination of chemical oxygen demand, that is called COD by titration. Now, first of all, you have to know what is COD. COD is the amount of chemical oxygen in milligram required to oxidize all the chemically oxidizable substance that may be organic, that may be inorganic, that may be bio-waste, that are present in 1 liter of sewage wastewater using suitable oxidizing agent like acidified potassium dichromate. It is generally expressed as milligram per liter or ppm. Now there are different organic, inorganic or bio waste, like organic material like different carboxylic acid, different carbonyl group, different aldehyde ketone that may be present, different inorganic substance like some chloride, some sulfate that may be present, bio waste like protein, amino acid that may be present. So we have to determine the amount of chemical oxygen. Why it is called chemical oxygen? Because this oxygen is provided by potassium dichromate chemical itself. In case of dissolved oxygen or biological oxygen demand, we are getting the molecular oxygen as O2. But here we are getting the oxygen from potassium dichromate. That's why it is called chemical oxygen. Now, this test is widely used to determine the degree of pollution, efficiency of treatment plant, pollution loads, and provides a rough idea about the biological oxygen demand. Now, potassium dichromate is the most suitable reagent used over here because it is completely oxidized all the organic material, it is relatively cheap, and it is easy to purify. Now, what is the principle? The principle is the water sample you want to check is refluxed in strong acidic solution with a known excess amount of potassium dichromate. Now, after the digestion or after the reflux, what the remaining unreduced potassium dichromate is treated with ferrous ammonium sulfate. That is, first of all, you are taking excess amount of potassium dichromate, and then you are adding the excess amount of potassium dichromate to your wastewater. Now, some of the potassium dichromate is getting oxidized by some of the potassium dichromate is exhausted because it is reacting with your wastewater sample, and some are remain as it is. So you are, by back titrating with ferrous ammonium sulfate, you are measuring the amount of potassium dichromate that remain unreacted in your sample. This gives us the oxidizable organic matter in terms of oxygen equivalent. Now, there are one acid catalyst mixture that we are going to use in this titration. It is the mixture of sulfuric acid, silver sulfate, and mercuric sulfate. Now, what are the role? Sulfuric acid behaves as an oxidizing. It helps potassium dichromate to behave as an oxidizing agent, and it provides the nascent oxygen, which further oxidize the sewage present in the wastewater. Silver sulfate acts as a catalyst and helps in oxidizing organic and biomaterial. And there are some chloride ion that must be present in the wastewater that may hamper the role of silver sulfate because silver chloride will be precipitated out. Now, mercuric sulfate prevents this precipitation of the catalyst silver sulfate by reacting with the chloride ion. It is converted to HgCl4 2-, which is water insoluble. Thus, it is preventing the chloride ion to react with the silver sulfate. Now, it is a kind of redox reaction. What is redox reaction? Redox means reduction and oxidation takes place simultaneously. Now, what is a redox indicator? Here we are going to use a redox indicator, that is Ferroin indicator. Now, you have to know what is the definition of redox indicator. First of all, we read in electrochemistry that electrode potential is the parameter which changes during the course of titration, and magnitude of the change is maximum at the time of equivalence point. So the indicator used for redox reaction must change its color due to sudden change in electrode potential of the system at the equivalence point. Such indicator is known as redox indicator. See, this is a reducing agent, this is the oxidizing agent. Some redox indicator is present over here. Its electrode potential must be like that. It should change during the equivalence point. Now, certain organic compounds that are capable of undergoing oxidation reduction reaction and the color of the oxidized form of the indicator is significantly different from that of reduced form may act as a redox indicator. Now, we all know this equation. We are getting this equation from the Nernst equation. E indicator is equal to standard electrode potential of the indicator plus minus 0.059 by N. N is the number of electron that is exchanged. Now, from this equation, it is clear that the potential at which a color transition will occur depend on the standard potential of the indicator system. So, the transition potential of the redox indicator must be equal to or near equal to the equivalence potential of the system such that it can give an accurate endpoint at the equivalence point. Here we are going to use the ferroin indicator. Ferroin is 110 phenanthroline compound, and it is capable of forming intensely colored, highly stable complex with iron 2+. It generally forms a chelate complex with iron. Now, this is the color change. This is the complex. This is a picture of the complex that 110 phenanthroline is forming, reacting with iron 2+. It forms a chelate complex. Now, phenanthroline, when form chelate complex with iron 3+, it is giving a pale blue color. But if iron is reduced to iron 2+, ferrous ion, then the red color will be reddish brown, and E0 reduction is equal to 1.06 volt. Now, coming to the test procedure. First, we will take a round bottom refluxing flux. In refluxing flux, we will put 1 spatula of mercuric sulfate, 10 ml of sample water, 5 ml of potassium dichromate, 15 ml of concentrated sulfuric acid. Then we will add some amount of silver sulfate in this solution. Then we will shake well and we will reflux for 2 hours. After cooling, a little amount of distilled water to the, we will add little amount of distilled water to the flask through the condenser. Now see the reaction change, see the color change. First the sample, this is the color of the sample. It is orange in color before digestion. It will give the color of the potassium dichromate. After the digestion, it will change its color because some amount of potassium dichromate is getting reacted with the sample. So just before the end point, the color will be pale blue. Why? Because ferroin at +3 state gives the pale blue color. Now, when there is no potassium dichromate present, in the solution, it is getting reacted. Then ferrous ammonium sulfate is coming into play. Then ferroin will form a stable complex with iron 2+. Ferrous ammonium sulfate. Iron is coming from ferrous ammonium sulfate. That iron 2+ will form chelate complex with the ferroin indicator, and at the end point, it will give a reddish brown color. So next step is to titrate the solution of the flask using ferrous ammonium sulfate and ferroin indicator. End point of the color is greenish or greenish blue to reddish brown. Now for the blank, what we will take in place of sample water, we will take 10 ml of distilled water. As there is no chemical oxygen demand for distilled water, as there is no soluble waste present in the distilled water, it will give the whole amount, whole potassium dichromate amount will remain present as it is. So from the blank, we will get the amount of potassium dichromate that is originally present in the solution. So for blank 10 ml distilled water, instead of the sample we will use, rest procedure will be the same. Now this is the calculation part. So COD we will express in mg per liter or ppm. It is nothing but A minus P into N into 8000 ml per ml of sample taken. So it is A is equal to ml of ferrous ammonium sulfate required for the blank, as because total amount of potassium dichromate present over here, so amount of ferrous ammonium sulfate will be more. B is the ml of ferrous ammonium sulfate required for the sample. As in our sample, there are some waste material present, organic, inorganic or bio waste present in the sample. So some amount of potassium dichromate will get reacted with that sample. So we cannot measure what amount of potassium dichromate is getting reacted with the sample bio waste sample. We cannot measure it directly. So from back titration, we are measuring it. So 8000 is the conversion factor, that is the equivalent weight of it is the conversion factor to convert the whole thing to the equivalent weight of oxygen. Now I am showing you how we'll do this practical. See, here first of all we'll select the test. Select the test as COD. Then see, we'll select the sample, water sample. Water sample we'll select as blank. First we'll do the blank titration. Here procedure is written. Here we are adding mercuric sulfate, water, potassium dichromate and silver sulfate and mix thoroughly. Then we will reflux. For refluxing we have to, then after refluxing we will titrate the excess potassium dichromate with ferrous ammonium sulfate using ferroin indicator. Now before titrating we have to reflux. For that we are switching on the mantle. See, here time is changing. Here time is changing and it is giving some color. So now we can start the titration. For titration we have to set different parameter. Blank, we have taken blank over here. Normality I am setting to 0.5. Speed of the titrant I am taking is in a speedy manner 0.9. See, here titrant is ferrous ammonium sulfate. You are titrating the whole material against ferrous ammonium sulfate. And indicator is ferroin, which is a redox indicator. I am already discussed. So I am starting the titration. See, the sample present is bluish green in color. It will change to reddish brown. Then we will stop. So it is undergoing the oxidation reduction reaction. When it will show reddish brown color, then we will stop. Now the reaction is taking place. We will stop when the color will change to reddish brown. Now we are stopping. Again we have to set the parameter. How? We will reset the parameter. Again we will select COD. Now in place of blank, you can choose tap water or well water or domestic wastewater. I am choosing here domestic wastewater. All the reactant are the same. That is mercuric sulfate, potassium dichromate, silver sulfate. You are adding sulfuric acid. You are adding and mixing thoroughly, and you are switching on the mantle. Time is taking for half an hour. Then you should start titration. Again, I am setting the parameter. You are taking domestic water. Normality should be same as before, 0.5. And speed of the titrant you can vary. I am taking here 0.9. See, here the titrant is ferrous ammonium sulfate and indicator is ferroin, same as before. Again, I am starting with domestic wastewater. Again, the color will change to reddish brown. Then I will stop. So I am stopping over here. So here I am getting the titrant used 2.7 ml, and at the first time I was get the titrant used as 5.1 ml. So so again I am returning back to my previous slide. So here you can see. So for A we are getting, for blank titration we are getting a value that is 5.1 ml. And for B, that is the titration with the wastewater, we are getting a value that is 2.1 ml. So A minus B will be 5.1 minus 2.1 ml. And N is the normality you have set as 0.5 normal, and 8000 is the conversion factor. Thus, you will get the COD in terms of mg per liter. Now, these are the advantage of COD test. COD test results are available much sooner than the biological oxygen demand test. COD test requires fewer manipulation of the sample. COD test oxidizes a wide range of chemical compound and it can be standardized more easily. So now we can understand how we perform the COD test. Thank you all for your kind patience.